Yeah, I want to examine a little bit, talk a little bit more about integrating with respect to y, because I mean, it's easy, if we can do the antiderivative, it's easy to do the integral with respect to y, but what does it really mean? That may be more important to us in the very near future here. So let's talk about a couple of things. First, let's start with the integral with respect to x, the one we're familiar with here. So 0 to 3 x cubed dx. Like I said, the integration part of this is very simple. You do the antiderivative of x cubed, which is 1/4 x to the 4th, and then evaluate that from 0 to 3. And so that's 1/4 times 3 to the 4th minus 1/4 0 to the 4th, which is 1/4 times 81. 81 fourths minus 0, so it's 81 fourths. Okay, so when we typically when we ask what's the meaning of that, we're talking about with the graph, and of course we know here the meaning of that is if we look at our function y equals x cubed here, what we're talking about is the area between the curve and the x-axis, net area in some cases, but here we're going from 0 to 3, so roughly speaking we're talking about this area right in here, right? Now, one other element that they'll want us to look at here is they'll call it the typical rectangle. And this goes back to what we first began, when we began talking about the area under the curve. We use rectangles, right? And so what that typical rectangle is referring to is one of those, draw one of those approximating rectangles is basically what that what that means. So if I was going to do this with rectangles, and you don't have to choose any certain width. Usually they do them narrow rectangles. But if I was going to approximate this with rectangles, I'd be talking about a rectangle like this. Like I said, it doesn't have to be any specific width, but that's what they refer to as just, if I was going to approximate this with the rectangles, and you can use left-hand endpoints, right-hand endpoints, it doesn't really matter. They're just interested in showing the typical rectangle would be looking like this. Now, that gets to what we really want to talk about. So if they ask for a typical rectangle, it's just drawing in something like that, okay? Now, let's talk about then the meaning of this integrating with respect to y. Like I said, it's going to be easy to, in most cases, to do this. All right, so let's say we go 0 to 4, and then we're integrating y plus 5 dy. Well, the calculation of that is not that difficult because it's addition. All we have to do is the power rule. It's 1/2 y squared plus the antiderivative. That's what we're doing there. And then the antiderivative, add in the antiderivative of 5, which is 5y. Go 0 to 4, and that is our integral. And then, of course, the 0. Plugging 0, you get 0, so what is that? 28. Half of 16 would be 8, plus the 20, so you have 28. Is that right? Is that right? Anybody believe that? Okay, now, the meaning of that. Well, if I'm integrating with respect to y, of course, what I've done is I've changed things around. several things. First of all, so over here, I graphed the y equals x cubed graph, right? I did that here. What's the equation over here? Well, no longer do I have a function of x, I've got it as a function of y, right? So this was a function of x in terms of x. This is a function of y, which if I wrote that kind of in the same line as this, I don't have y equals y plus 5, do I? It's x equals y plus 5. If I'm talking about that basic Cartesian coordinate system. This would be our function, but it's a function of y, which means that gives us our x values. So this is our function here is x equals y plus 5, right? And so that's what I've got to graph here to get the meaning. All right? Okay. So x equals y plus 5. Of course, that is just a line. Let's see, the x, if I did the x-intercept, it would be, the y is 0, so x would be 5. And then if I do the y-intercept, the x is 0, so that would be, solve x is 0. That's where I'm getting that. That would be y equals negative 5. Solution there. So this is how I'm getting the graph. But it's just a line because it's x to the first and y to the first. You know, you get some sideways stuff going, but we'll talk about a few of them later on. But anyway, just getting the basics down here. Now, so that's the graph. But no longer are we talking about between the curve and the x-axis for various reasons. If you break it down here, remember the dx and delta x, those are the same. So here we're talking about not a delta x, we're talking about a delta y, change in y. So, and if you remember, that's kind of the width. Without going into a whole lot of detail here, what I'm doing is I'm basing this off of the y-axis now, if you will, because I'm changing the width of these are going to, remember the width over here is the delta x, the width over here is the delta y, so it's the change in y's. And so the other thing here, also probably easier to understand here, is these are y values, right? And so I'm not talking about from x is 0 to 4, I'm talking about from y equals 0 to 4. And then again, change in y, so these are going to be my width. So long story short here, this is, when I integrate it with respect to y, I'm not finding the area between the curve and the x-axis, I'm finding the area between the curve and the y-axis, okay? So when I integrate with respect to y, you are finding the area between the curve and the y-axis. So that's probably sort of makes sense, hopefully. Between the curve and the y-axis. All right? Now again, if they ask about the typical rectangle, so that area is 28. So they ask here about the typical rectangle. Well, I'm going from the y-axis up to the curve, or it could be down to the, if it's, we got this range down here, it'd be from the y-axis down to the, or over to the left here. But anyway, the typical rectangles here are going to be sideways, aren't they? Because if I was going to approximate this area, I wouldn't go from the curve up to the here. I would go from the y-axis out to the curve. So the typical rectangle here would be a sideways, if you will, rectangle. That, if I was going to approximate this area, that's the way I would do it. All right? And so, one of the key points here that we need to understand, I mean, we were told here we're integrating with respect to y and respect to x, but what you need to notice here, yeah, if I integrate with respect to y, I'm talking about sideways rectangles. If I'm integrating with respect to x, the rectangles are up and down, okay? Because sometimes it won't tell us integrate with respect to y or integrate with respect to x, and this is how we're going to decide. We're going to draw in a rectangle. It's going to be, we're going to say, well, it's going to be easier to do the rectangles like this, and so that's going to tell me integrate with respect to x. Or it's going to be that it's going to be easier to integrate with respect to y, or do the rectangles like this, and so that's integrate with respect to y. Okay, so integrate with respect to y, you got sideways rectangles. Integrate with respect to x, the rectangles are up and down. So that's one of the key things that hopefully you kind of understand at this point. Okay, it'll come up more later. All right, any questions about that?